Yeah, thanks for inviting me to the talk, and I appreciate the opportunity to talk about it. And I think it's a very nice slot, particularly after Bratislav, because it talks about how to link neurobiological data to electrophysiology in this example, but it could also relate to fMRI. So I'm going to focus or speak about two aspects. One is just maybe the general framework about how to integrate cortical maps and electrophysiological data, just giving a high-level overview on DCM and then parametric and behavioral base. And then in a second part, we're going to speak about how we related neurotransmitter receptor densities to intracranial EEG. So that's a worked example with some probably interesting findings. So coming to the first bit, I mean, it's a large question, obviously, how to relate maybe clinical or macro data like electrophysiology to neurobiological data like brain maps and neuroreceptor maps or whatsoever. So one way is to use generative models or hierarchical generative models like here shown a 4-population neural mass model, and then use 2 steps, and I explain them in a little bit more detail later. So the first step is to basically fit the models to electrophysiological data and estimate a set of parameters in the first space without neurobiological data. And then the second step, use the neurobiology or the neurotransmitters in our case to basically provide hyperparameters and then do a parameter optimization, and by that kind of makes the models fit better and avoid misfits and maybe fitting in local optima, because DCM is not a full parametric search, it's a heuristic in some way. So to explain or just give a high-level overview about the 2 modeling steps. So the first modeling steps uses DCM or dynamic causal modeling as a Bayesian model fitting procedure, basically taking means as well as the distribution. So it takes a level of uncertainty into account for this canonical microcircle, like a neural mass model with 4 populations which are loosely related to different cortical layers or dominant neural populations in different cortical layers. So each of the populations is described, and I just for completeness I included that with an ODE here, and it basically describes the tuned synaptic impact and some damping and decay. And then in the second level, basically we can use the covariates, and in our case we use different neuroreceptor densities and kind of relate them to a specific model. So, for example, here model 1 can have the covariate, for example, only AMPA receptors, and then covariate 2 could be like NMDA receptors as well. So, this can make our model space, and I will show that and illustrate this further down in the talk. And then the second is basically how is the second level parameters estimated. So PEP is basically a general linear model to test hypothesis. It's not, it's again like not exact, but it's a very nice way to test hypothesis and include covariates. And that's done here. So you say basically a different design matrix for this model with different recordings, and then the covariates and the covariate values. Just coming to the illustration of the approach using neuroreceptor densities and intracranial EEG. So what we did here, similar as I described previously in the kind of outline, we used intracranial EEG, and this is nicely coming from the Frauscher, atlas, the normative atlas. And we used DCM fitted basically the 1,770-ish individual recordings from depth electrodes and cortical strips and grids with DCM, and derived or inverted a baseline DCM which had no neurobiological data included. So that's the step. So coming from basically taking off the shelf the DCM, and then inverting the parameters. And the second step then, we used the receptor densities, and that was Ulrich data from Carl Salz and Nicola Palomero-Gallagher's lab. And we used the different variations of the neuroreceptors. So we only used selected neuroreceptor densities, and then we also used principal components to capture variance across the receptor densities, which are, have some similarities, and use that to define a model space. And tested this model and tested what variation of data or what specific neuroreceptor data actually improves the models overall. And then as an outcome, specific outcome here, we had a cortical atlas of normative DCM canonical microcircular coupling parameters, which can be used in other modeling exercises. This is just one specific outcome here. So as said, the one bit was the EEG traces. We used them not in the time domain, we used them in the signal, in the frequency domain as a kind of lower level descriptor. And this is just to illustrate the specific, say, oscillatory peaks and different cortical lobes. And then we use some canonical microcircuit as described as a for population neural mouse model, with here basically indicating the different cell types like superficial pyramidal neurons, spiny stellate cells, inhibitory interneurons, and deep pyramidal cells. What we got then is basically the model fit, the initial model fits for this about 1,800 recordings, and you see, you see some errors, and our aim was basically to improve these models with neuroreceptor data. So in the second step, we included the neuroreceptor densities in different constellations and variations, and I see some aspects of the graphics might be missing. So I see that in the next. So hope it comes up correctly. Otherwise, I'm just gonna explain it. So here, basically, in the study, 15 neuroreceptor densities, and Brothers have alluded to that a little bit, which was also related to some electrophysiology in MEG by Justine Hansen previously. So we used that data and variance of the data, and what we found, and you see the error which I saw. We found some correlation between the receptors and thought maybe a low-level descriptor of the receptor densities might be more appropriate measure or an alternative measure, basically, or data point or feature to be included in the model. And then we used also the receptor density, basically principal components in the models. What we also saw, and that's in kind of also related to, that's bad. I'm sorry for saying that because you can't see the next bits, which is unfortunate. But what I wanted to show here, and I show you, is that you have actually good correlation between the power in the alpha band spectral density, which is shown here, and then the different receptor densities already, which is indicative that there might be an overlap between the topography of the IEG signal or the IEG spectra or the cyclicality of the IEG spectra and the receptor density distributions, which is really unfortunate that this doesn't come up correctly. Sorry about that. But so to follow through, what you see here and what is is the full model space. So what we did, we basically, as I said, just inverted the baseline model, which is the black model on the far left. Then we had the different candidate receptor models. So we had the 4 individual receptors, AMPA, NMDA, GABA A, GABA B, and then we had combinations of receptor densities. So we had AMPA and NMDA and so on and so forth. And then we had the principal component-based models. And then we had, for the winning principal components-based model, we had null models here. And described earlier, or maybe was alluded to yesterday. So difference so these are models compared with a base factor, with a log base factor, and a base factor bigger than 5 basically indicates that one model is significantly better than the other model. So when you see values like 85 or 23 or 285, that's magnitudes better, and it's highly significantly better than the baseline model. So basically what you see is that all models are better than the baseline, so they include some very relevant information. But yeah, so then the winning model was including 4 principal components, which explain about 80% of the variance of receptors across the brain. So yeah, and you see that here when we did the model fitting, including the receptor densities, all the principal components, we got a much better basically model fits. So there was only one which wasn't great. I mean, it was still good, but it wasn't like nearly perfect. So you see that here compared to the standard DCM. And what we got from that, we got basically price, which then can be used for other models. And we did a small test with a fairly well-known ERP, so the mismatch negativity, and that was a model which was replicated multiple times, and is a good kind of baseline model. So what we did here, we basically assigned the price which we derived in the previous step to the different network nodes here in the MNN model to see if we get basically a better model fit here as well for a different modality and different modeling regime, and also for a network model. So we got good fit, and as you see here, basically we had different ways of including the data. So we included basically with a Gaussian kernel, we included different, numbers of say, price around the specific MNI location to see maybe, what kind of magnitude and what kernel might be best suited to include the price. And we got one here. And that's also significantly better, as said, compared to the baseline model. Just to summarize it, so the way, so I try to illustrate two things here. One is the general approach, how basically one can integrate a generative neural mouse model and neurobiological data, and I illustrated that then with neuroreceptor densities. And as I try to say, and I will allude to that again a little bit, this is one way. So obviously there's a lot of data, and eBrains has a lot of availability. Neuromaps has a lot of different interesting data sets, and so this is an interesting, I think, approach to quickly integrate a very flexible dynamic model with a lot of neurobiological data to test different hypotheses. And then, as I showed in the last slide I had, is we use this price derived in our case to a well-known paradigm, and that worked and improved model fit. So that's good. I'm going to just very quickly go through the outlook. I mean, obviously, as with all modeling exercises, there are various aspects you could improve, and how you can actually use a model. And so I'm just going through. So one is basically using the model to just generally make better predictions. So one can just go and take the price and this exactly modeling approach and just see how it improves different modeling exercises. As the second thing is, which we are doing, is then using that for pathologies, for example, epilepsy, and also with Nicholas' data, who has basically histological data and neuroreceptor densities also for epilepsy patients, so that we are using. Then refine definitely hypothesis and just not looking at the general kind of aspects we looked at, but very more detailed hypothesis, and then look for parameter identifiability. do further integration and then doing more network models. And so, with the last 20 seconds, I just thank, collaborators and advisors and supervisors and so on. So thank you for your attention.